All right, so I think we can get started. So today we'll give a tutorial talk. I know it's weird. I'm not doing CV, but I just try to submission, to CVPI, CVPR and get accepted. I want to get some feedback, but I was like, "Are you serious?" Because I've not been doing CV, but I think it is still good for everyone to know some of the graph neural network in CV because I know there's some application, great application in CV, right? So can you hands up how many guys are using graph neural network in your work? Some of them. How many beginners? Oh, already. Also, I think it's pretty good to know. So it seems like half of you are beginners. Maybe you're just humble, right? I don't know, but yeah, we have good audience. So let's get started. So my topic, it seems is not directly related to CV, but I will share some of CV applications using graph neural network. My title is Unifying Spectral and Spatial Graph Neural Network, because sometimes, hello, 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 hello. There's some of hello. Oh, works. Hello, okay, works. So sometimes, all right. All right. So I think it's still exciting for you guys. Maybe you can consider using graph neural network in your own work. I think because it's a very popular machine learning tools, right? Except a large language model. So if you just come here, so please scan the QR code, and there's an online Q&A, and I can collect questions along the way, and I promise I can answer most of the questions during the tutorial or even after this tutorial. I think it's a better interaction mode between us. So I'm Zhi from the Mississippi State University, assistant professor, and this tutorial is collaborated with Dr. Lei Zhang and Dr. Liang Zhao from Emory University. So we are guys who are doing graph neural network for the past few years. So here's the agenda. We have two separate sections. In the first half, we'll talk about some preliminary. I think it's pretty good for half of you guys, most of the guys if you have, because some of you are beginners. But I will talk the preliminaries under our proposal framework. So it's kind of different. In the second half section, we will talk about the proposal unified framework. And between them, there's a break of 15 minutes. And after the tutorial, there's a 15 minutes Q&A. So just a Q&A, and you can join online, and you can also join by typing the numbers 96 41 911, 96 45. Sorry, 96 45 911. Easy to remember. So we can talk anonymously, and the questions can be answered during the tutorial. So, all right, so let's move to the first section, which is the background of unifying framework for graph neural network. So this is normal introductions, graphs everywhere. So we have, in the past several years, there's COVID-19. So when you connect the transportation of the disease, it can be a disease transportation network, right? There's a social network, Internet of Things, brain network, there's a connection of the region, which is also active. And also there's a popular network in the chemistry structure, which connects the atoms of the chemistry compound, the Internet of Things, Internet, and also as well as a particle system in the physical system. So I think this may be interesting to some of you because why I need to listen to this talk. Actually, I'm not doing CV. I'm open to any applications using graph neural network. So here's we will give like a list of a possible application using graph neural network.
Yeah, so both graph and graph neural networks have been widely used in CV. So maybe one of the most important application is the scene graph generation, right? So given the input image data, you can segment the data into different objects. So in order to do the scene graph generation, you can treat the objects as nodes. Then the goal of the scene graph generation is to generate the relationships between the objects. The relationships will be considered as edges in the graphs. In most of the scene graph generation tasks, people use graph neural network models. And with the help of the graph neural network model and the scene graph, we are able to solve many problems more efficiently and more effectively. For example, for doing the image and video captioning, if we are able to generate the relationship between the objects in the image, we are able to get a potentially better quality image and video captioning. And another example is the structured reasoning for visual Q&A. So for this task, we are not just given a image as input, we are also given a question about the image. So with the help of the scene graph, we can represent the input image as a graph with objects, with nodes representing the objects in the image. And for the question in the format of text, we can also represent the question as a graph, and the nodes in the scene graph and the nodes in the text graph can share some nodes. So by doing so, we can get better quality answers for the Q&A tasks. So for the scene graph, not necessarily we want always start from scratch. In this application, it's an application of the image classification. So in this application, we can potentially use the existing mature knowledge graph and in help with doing the image classification. For example, in the image, there's an animal, and we can recognize the different components of the animal. And instead of generating the scene graph from scratch, we can use the existing knowledge graph and do some reasoning such that we can do the classification task more effectively. So those are the examples of the graph neural network used for the graph structure in the data. However, the graph structure also exists in the neural network architectures. For example, in Dr. Xie's work, as you can say, the authors generated random graph structures as random neural network architectures. They found that by doing so, even those neural network architectures look weird, but they actually can achieve a good performance on par with many of the human-defined, human-crafted neural network architectures. And similar to that work, some other researchers proposed something called the relational graph representation. And the idea is that they want to represent all the neural network architectures in this kind of relational graph representation. And if you are able to do so, you can put you can just represent every neural network architecture in the distribution of graph structures. And if you are able to do so, it is possible that you can pinpoint the sweet spot in the distribution where the neural networks perform better than the others. This is very helpful for the neural architecture search. And this is a very similar work. So in this work, the authors used a graph convolutional component for encoding the graph structure of the graph neural network model. And they wanted to predict the latency and the accuracy of the neural network model here, such that even without training the model, you can have a rough idea how the accuracy and the performance will be like. And more than that, the graph neural network model has been also used as a hypernetwork. A hypernetwork is a neural network model that can generate the weights of another neural network model. It's different from the concept of hypergraphs. Hypergraphs are the graphs where one edge can connect to more than two edges. So anyway, this work is pretty interesting because it can be very helpful for transfer learning. So those are all the applications in computer vision. Yeah.
So I guess some of you might be familiar with the graph neural network, right? So here I just listed some of them. The proposed from, for example, heat diffusion proposed based on the page rank, the random work, graph length. Actually, there's many more, right? So one question is, there's a lot of in the market. If I'm a CV application, right? If you apply them in a CV application or other applications, how I choose it, right? It's like in your grocery. Here's a tomato, bad tomato, good tomato. How can you distinguish the good from bad one, right? So this is the market, right? And the question is that they are different, right? They're from different words, right? You see the terminology, they are very different. How can we compare them directly? There's no way. So here is the motivation of our proposal. We want to propose something that can look into each single graph neural network using a unified framework so that we can compare each of the graph neural altogether. So I marked blue and red, which means one is proposed from the spatial domain, spatial idea, some are from the spectral ideas, and there's a two category, and we will use the two category to do. But even so, they are different, right? Each of them are different. So the challenge is that, like I said, there's a lot of in the market, and I want to take one of them, right? I'm not a researcher in this domain. I just want to take one of them. Can you tell me a matrix or maybe just a simple conclusions, which one to choose, right? But the challenge is, actually, there's some of, but I would say there's no completely uniform, especially theoretical framework to compel them, right? So in this tutorial, I will give you one possibility. Even it is not the only one, but we will show you guys that our proposal framework is pretty unique and provides you a unified framework. Maybe you can propose a new graph neural network and use this framework, or maybe you can choose graph neural network from the market, right?
There were actually some attempts in unifying graph neural networks in each domain, either in spatial domain or in spectral domain. One of them was related to the expressive power of neural network models. The expressive power is that the ability to distinguish different graph structures. One special case is we want to evaluate graph neural networks by judging if they are able to differentiate the graph isomorphism. Here are two examples. In the left example, as you can see, there are two graph structures. They are totally different. If we have a powerful graph neural network model, our expectation is that it is able to generate different representations for the different graph structures. That is our expectation. And here is another pair of graph structures. Even they look pretty similar, but they are similar because they are indeed the exact same graph. They just have different ordering of nodes and different layout. So for this kind of graphs, we call them graph isomorphism. And for graph isomorphism, our expectation is that we want the graph neural network to generate at least the same representation because they are the same, right? So this is one of the existing work for comparing graph neural networks. And the way they are able to do that is that they first define graph neural networks as two simple functions. One is the aggregate function, another is the readout function. So by doing so, their conclusion is that the GNN models are at most as powerful as the WL test. WL test is one graph isomorphism test. It can be considered as one algorithm since it's very simple and it's very similar with graph neural network model. So we can treat the WL test as one standard. So another conclusion was that the upper bound that we can achieve is that both the aggregate and the readout functions are injective multi-set functions. So what is the injective multi-set function? One injective function is a function where every possible output has at most one associated input. So if the answer is 13, you can only have one input that can generate the result 13. So if your graph neural network model can meet this standard, then it has the maximum expressive power. So on the contrary, the graph convolutional neural network model, maybe one of the most famous graph neural network model, actually does not meet this standard because the graph convolutional neural network has the mean aggregation. So mean aggregation is not an injective function. So as a result, the graph convolutional neural network does not reach the maximum expressive power. So here I have talked about the relationship between the spatial graph neural network and the isomorphism. This is related to the expressive power of graph neural network models. As I mentioned, they describe graph neural network models as the combination of aggregate and the readout functions. However, this description is only defined in the spatial domain. The spectral graph neural networks cannot be described in this way. Fortunately, there is another work. By the way, the work who did this analysis is called How Powerful Are Graph Neural Networks? There's another paper that is called How Powerful Are Spectral Graph Neural Networks? So in this work, apparently we cannot analyze the graph neural networks by analyzing their aggregate and the readout functions. So in this paper, the authors need to analyze the spectral filters, which is what we use for spectral graph neural network models. But as you can see, in both work, people have different systems, have different ways of analyzing those methods that prevent us from having a better understanding of both the spatial and the spectral graph neural network models. Not to mention that both work have some shortages. For example, in the for the spatial graph neural network models, all the assumptions is based on that the graph neural networks have discrete features, and the conclusions does not work on the graph neural networks with continuous features. But as you know, in the real world applications, most data, node data can have the continuous feature. And another fact is that even we are able to achieve the maximum expressive power, in other words, having the same expressive power as the WL test. WL test itself is not perfect. It cannot detect 100% graph isomorphism. So in other words, for many graph isomorphism pairs, it is possible that even the WL test cannot differentiate the differences. And for the spectral graph neural network models, the conclusion was that the spectral filters are universal approximators when satisfying two conditions. I won't go into details, but this analysis is only limited to spectral graph neural networks without nonlinearity. But as you know, in most neural network models, we do prefer to use the nonlinear activation. So those are the shortages. According to our survey, existing surveys and many of the theoretical analysis focus on either the spatial or the spectral graph neural networks, but not all of them. So in this tutorial, later we will introduce a framework that look like this. And our goal is to unify both of the spatial and the spectral graph neural networks in the same framework. Yeah.
All right, so let's move to the next section, which is preliminary study. I will introduce it is introductions to graph convolution. I think you heard a lot about the graph convolution, but here we will reformulate the graph convolutions under our proposal framework. So let's recap the convolution layers in normal CNN that's often used in computer vision domain, the CNN. So as we know, for example, here is the 3x3 pixels. So we have the 3x3 kernels, right? And we just time them up with 2D convolution, right? Actually, it's pretty easy. It is time-wise, it's element-wise multiplication and sum of them, right? So what we need to do is that we just input like all the blue pixels, which is the patch of the image, and we want to learn the green pixels, which is our kernels. And here we just have 3x3 parameters, right? But you can increase the channel, you can increase the number of image patches, right? So finally, we will update the P5 in the middle, in the center of the 3x3 pixels, with the average of its neighbors, right? This is what we do, right? Or intuitively, we will show you a, pick up some of the popular animation. We just, ask the kernels to scan from left to right, from top to 10, up to top to bottom, and just train out the optimal kernel parameters, right? So similarly, if we see this similar things in graph domain, which is different. So in graph domain, you see there is a C, A, B, C, right? And here, for example, we have three training instance, A, B, C, and its neighbors, or their neighbors, right? A and its neighbors, B and its neighbors, and C and their neighbors, right? Each of them is one training instance in graph neural network, right? But unfortunately, we cannot use a normal CNN or normal convolution layers in the previous slides, right? Because the question is, they have a dynamic number of neighbors, right? And we're doing machine learning, we use machine learning, we hate ununified dimension, right? So if we can do that, there's only one way. If it is in I mean all the nodes are in different dimension, we first convert it into unified dimension, and then we can do whatever we want to do, right? Followed by MLP or whatever machine learning method, right? But we cannot directly do this, right? So that's why we need to come up with a method that convert this nodes with unified dimensions to unified dimension. So traditional convolutional definitely does not work. So this is the motivation of the traditional graph convolution, right? We will distinguish convolution neural networks convolutions and graph convolutions in our proposal.
Yeah, so the way we are able to do that is through the convolution theorem. The theorem says that the Fourier transform of the convolution of two functions is equal to the pointwise multiplication of their Fourier transforms. So this is the convolution of f and g, right? And this is the Fourier transform of the convolution itself. And this is the Fourier transform for the function f. This is the Fourier transform of the function g. They equal with each other. This is the pointwise multiplication. This is according to the convolution theorem. And the intuition of this transformation is that the space convolution equals with the frequency multiplication. And we can do a little tweaking. We can remove the Fourier transform on the left side, and we add a inverse Fourier transform on the right side. And then, this is the convolution. This is the convolution, and the right side is equal with this convolution. And the way we are able to do convolution for graph structure data is not by directly calculating the convolution in the spatial space. Instead, we do the convolution and the inverse the Fourier transform and the inverse Fourier transform in the spectral domain, such that we can overcome the issue that we just discussed.
So here is an illustration for graph convolution. It's different from the CNS convolution because I was taught it utilizes the convolution theory. So first, we need to convert everything in spatial domain into spectral domain, so that we can perform the convolution theory, or we can make everything in the same dimension. We like it, right? Before transformation, they are not in the same dimension. After this transformation, I mean, from the spatial domain, from here, right, from left side, right, everything is in the spatial domain. The connection, then the graph structure, which in the form of adjacent matrix, graph Laplacian matrix, right? They are in a spatial domain. The graph signal, each node, for example, if you're in a social network, it is female, male, how many followers, right? That's a node attribute. They are in the spatial domain because they have fixed meaning. It's easy to understand, right? So first step is we transform those data by graph Fourier transform, so that every data originate in spatial domain, and after the transformation will be come into the spectral domain, right? So if we go back, you see, so first the big F here is the Fourier transform, right? So this is our first step. Apply the big F. We can convert everything here into in the middle of them. So we go from spatial domains and we arrive at the spectral domains. Everything here is a spectral things, right? And secondly, we'll perform the element-wise multiplication, which is easy to do. And here actually is this step. It's a element-wise multiplication. Right? The second step is in the middle. It's the dot, right? So here we perform the element-wise multiplication, and then last step, we're good to go. Because things in spectral domain is not easy to understand. There's some of the technical meaning, but there's no physical meaning, right? So that's why we still need to perform the last step. We can transfer everything from the spectral domain because we finished everything. We have done the convolution in another way, which is the technical sound. We finished the convolution, and then we're good to go. We want to go back to the spatial domain. So everything is understood. Before the transformation, it can be, for example, it's social network. It can be the attribute can be the gender of the user, the photo of the user, maybe the money of the user or something like that, right? But after transformation, when everything is in the spectral domain, it's kind of a confusion, right? It is a technical sound, but there's no much of a physical meaning. So we need to perform the last step. We go back to the spectrum. So everything right now is physical. Everything is like before. So let's recap. So first we will do graph Fourier transform by big F. And then we perform the element-wise multiplication. And then we perform inverse the graph Fourier transform. So we can go back to the spatial domain, right? So by doing this, we unify the dimension, we finish the convolution in another way, and we get back to the spatial domain. So everything has physical meaning.
Yeah, so now the remaining question is how we define the Fourier transform on graph data, because as you may know, the Fourier transform in traditional research is normally applied on image data or time series data. So now we need to define the not only the Fourier transform, but also the inverse Fourier transform on graphs. And here's an illustration.
Yeah, so let's recap a little bit of spatial analysis. I assume most of you haven't learned this before. Is it any of you know this before? I think it's very popular when people talk about especially time series, right? This is very popular in time series, right? Where people is likely to perform the spatial analysis. And the first is the so-called spatial decomposition. Sometimes they call it eigen decomposition, the same thing, right? Two different names. So I pick up animation from the Wikipedia, I remember. Just a recap in case some of you don't know about it. So here we have a square signal, right? And by doing the spatial analysis and or say spatial decomposition, we can decompose the square signal into different components, right? Here we have this is a constant, right? We have a low frequency, component, middle frequency component, and high frequency component, and so on. And those frequency components right now are new basis. We are going into a new space, right? So we have a new basis. The only different thing is that we have actually unlimited basis. But of course, in practice, we just take first a few of them. Otherwise, there's no way to compute. But in theory, there is an unlimited dimension, right? What we need to do in the new space is we learn out of the new parameters or new coordinations, right? So here is you can treat those new bases as new x axis, y, and z. And along the x axis, how much values? How much is the parameters along the x? How much parameters along the new basis, right? So this is useful because we can recover from the right side, for the left side. We can just represent the left side by using the right side. So we can know, okay, how many high frequency inside, how many middle frequency, how many low frequency. So we can look inside it. So similarly, we can do it in graph, right? But kind of different. But the only similar thing that is we have a new basis. So first, we construct a new basis by the also spatial decomposition, but here is on the graph matrix, right? So in the previous slides, we can say we do it in single dimension, one dimension, right? But in graph, we can perform the spatial decompositions on the graph matrix, which is 2D, right? So you can check out the techniques on the 1D dimension. This is spatial decomposition on 2D dimension, actually it's a matrix. And also, if you're interested, there's actually 3D, 4D, and so on. So in this domain, in the graph domain, you can see that we first decompose the graph matrix into eigenvalue and eigenvector. So, this is normal things is an eigen decomposition. We got two outcome, eigenvalue, eigenvector, and we use the eigenvector as the new basis. If we visualize the eigenvector, it is look like this. You see the first eigenvector is actually, all red, which means it's constant. Right? There's no difference. You cannot use a constant to distinguish anything, but maybe it's good to have. Right? You can tune the final value or something. And you see the second eigenvector, there's some difference, right? Some region are red, some region are blue. So there's some emphasis, right? Actually, if you're familiar with the graph, this is the roadmap of Minnesota, right? Can you guess where the capital of Minnesota is? I guess here, right? Yeah, just somewhere around here. So it makes sense that okay. So maybe we can use the new basis here to distinguish in the north and south of Minnesota, right? And interesting, if you see the eigenvector 2, actually third eigenvector, you can see that we can distinguish capital region and the non-capital region, right? And so on. There's many more. Like I said, this is a spatial analysis. So the dimension is unlimited. But in practice, we will take a first few of them, right? Question? Hmm. Yep.
So my question is, what is your no spectral signature? 1, 2, 3, 4, what's your X1? Is this the no signature?
Oh, you mean what is the in here? What's the meaning of each node here?
Right. What's the meaning of the each here?
Yeah. That's a good question. So right now we are not doing so. So let's start from here. Let's start from the blue roadmap, right? It's just a connection, nothing else. There's no signal at all. It's just a roadmap. There's a 1-0 connection. If there's a connection between two nodes, we make a connection. We make a link there, right? There's only graph structure at this point. After this, we will introduce how we can incorporate the node attribute. But at this point, we just construct a new space based on the graph structure only. So that's the way we construct a new space. Right? We have the origin one. We have the origin one here, and there's associated graph matrix. So here it is a graph log matrix, and you can do graph agents matrix. That is similar conclusion. But let's use a graph log matrix because this is normal. Hello. Hello, hello. Hello, hello. Okay. So let's continue. So at this step, nothing special, just the graph structure. We use the graph structures, one from matrix, which is the graph log matrix, and perform the spectral decomposition to get eigenvector, and we use the eigenvector only to construct a new space. And by the way, each of them eigenvector is orthogonal, which means that they are different. There's no information overlap at all. So in each dimension, they are unique. Right? So like I said, if we can explain the third one, the eigenvector 2, as something or indicators, which can distinguish the capital region and some others. Right? So here we talk about, okay, right now we have singular. Left we have a graph structure, right we have a graph singular. For example, the singular is the traffic speed, for example, right? Right now, today at this point, I take a screenshot of the roadmap, and there's a monitor along the roadmap, right? So right now we have the features. At each node, there's a traffic speed or traffic volume, right? And we want to do one thing similar to the previous spatial analysis in the time series. That is, we want to represent the peak signal using a new space, right? So we have something to present. So the right pink signal is something like the swell signal in the previous slides. It can be whatever signals you want to present. I just show you an example, right? It can be whatever things you want to present. For example, we have a new signal, which is a roadmap. With the speed over the roadmap. And similarly, we can learn the parameters because we have already we have the eigenvectors, which is our new basis already. What we need to do in the next steps, we'll learn out new parameters in a new space, right? So here we represent it is not a W0, W1, W2, W3. It's something new because this is to be learned. It's to be learned. After we adjust in the W0, 1, 2, 3, we can recover, the signal. Right? So here we have, for example, we have 1.2, 3.5, some point something like that, and times each of the bases and sum up all together, and then we can recover any of the signal. Right. So that's the spatial analysis on the graph.
Yeah, so now let me walk you through the process of inventing the graph convolutional neural network model. So as I mentioned, we start from using the convolution theorem, which is shown here. So then our question is how we define the Fourier transform and the inverse Fourier transform on the graph structure. Those are from existing literature in the graph spectral analysis studies. And now I will just give you the answer. The Fourier transform on the graph for signal or function f is just the u transpose times f. And the inverse Fourier transform of the function f is u times f. And so now what is U and U transpose? It can be calculated in this way. So here, as you can see, there's an equation, and in this equation, L is the graph Laplacian. As soon as you know the graph topology, you can calculate the graph Laplacian by using this equation. Here, the I is the identity matrix, and the D is the degree matrix of the graph, the degree of each of the nodes in the graph. And A is just the adjacent matrix. I won't go into details why it's written in this way, but this is the conclusion, right? So as soon as you get the graph convolution L, then you can do the decomposition and get three matrices: the U, lambda, and the U transpose. The lambda matrix actually is a diagonal matrix with n eigenvalues. N is the number of the dimensions. U is the basics. It's the eigenvectors. So now, if we are able to get the U and the U transpose, we are able to do the Fourier transform in the spectral domain for the graph data. So putting everything together, now we reach this point, we can finally define the graph convolution operation, the convolution between G and X, because previously we have F and G, but in practice, normally we have the graph itself on the graph structure. Normally it's in the format of the node feature matrix. This is the N by D matrix. N is the number of nodes in the graph, and the D is the dimension of the features. And the G is the convolution kernel, which you may be more familiar with. And this is the graph convolution operation.
All right, so let's see how we can technically implement the graph convolution. So I use the same example, right? Minnesota road network and Minnesota's, for example, traffic speed over the road map, right? So one is a graph structure, which we represent by the graph matrix, such as HS matrix or graph Laplacian matrix. And the graph signal we just present because it's just one dimension, right? Graph signal, each point has only one single value, right? It can be, 30 kilometers per hour, something like that. So here, so let's perform one by one. So in the first step, so like say, everything is in the spatial, right? It's understandable, but unfortunately, they are not in the same dimension. So that's why, we need to perform the graph Fourier transform so we can make everything in the same dimension, right? So first step is perform the graph Fourier transform, and this can be implemented by left multiplying U transpose. And this is formally defined as the graph Fourier transform, right? X is input, it's the signal. X, for example, if there's I don't remember exactly the numbers of nodes there. For example, there's 2,000 nodes, right? So X's dimension is 2,000 by 1, right? So each point is one speed value, right? So 2,000 by 1. And the U transpose, because the U is the eigenvector, so its size should be n by n. And n is the size of the node number in the graph, right? We have L here, and we perform the eigen decomposition, get eigenvector, and also the eigenvectors transpose. Eigenvectors transpose, of course, is the same dimension as eigenvector, which is n by n. So for here, if we have 2,000 nodes here, U transpose dimension is 2,000 by 2,000. Right? So the first step in the red rectangle, right?
Clarifying function. So X is the node features.
Exactly.
So it would be the number of nodes by number of features.
Exactly. So you can have the two dimension, but here my example is only have one. Yeah, just one. You can have two, right? And many more, right? But to be honest, I just to let you know, it seems that in the graph single percent domain, they prefer one dimension only. And I believe in the seed work, the graph neural network, the GCN, the work is from 2019, because that work is inspired from the previous work, which is in the graphical signal processing. But the signal processing domain is only as I have reading many. I'm not an expert in that domain, but all the papers in graphical signal processing as I read so far, it seems that most of them are focused on the one single dimension. But of course, we are doing machine learning, right? We can do whatever dimension we want, and give a MLP, right? So here, of course, we use the traditional or classical definition. So here, x is one dimension, right? So x is one dimension, 2000 by 1, right? It can be 2000 by whatever, but here is 2000 by 1. And then U transpose is 2000 by 2000, right? It's eigenvector. So we finished the first step, which is about the Fourier transform, right? So before transformation, we're in the spatial. After this transformation, everything are in the spectrum, right? There's some technical benefit, but we are into a world that we don't quite understand because everything is spectrum, right? And the second step in the green, right? That is actually the convolution. The convolution defined in the convolution theorem. It's not the convolution in the CNN, because the CNN is a spatial convolution. It's the element-wise multiplication and the sum of them. And here is the spectral convolution. It's the convolution used in graph convolution, right? So, but which is pretty easy. It's element-wise multiplication, right? Because the rectangle, inside the red rectangle, the dimension right now is 2000 by 1. And the g theta here is 2000 by 1. 2000 by 1. So so between them, we should put a dot there, but it is element-wise multiplication. I mean, this one and this one, we're doing element-wise multiplication. And after this one is 2000 by 1, right? And we will make it as a diagonal matrix. So the shape will be 2000 by 2000. It's a trick. So we finished the second step, right? But we are ready to go. Because right now we are still stay in the spectral domain, right? Which is technically sound, but we don't understand what that is, right? It's a technical, there's a technical beneficial, but we still want to go back to the spatial domain. So we need to perform the last step, which is the inverse the graph Fourier transform. Formally, it is defined as left multiplying U dot. So left multiplying U. You see the difference between the inverse the graph Fourier transform and the graph Fourier transform, the first step and the third step. They're both left multiplying something, but the graph Fourier transform left multiplying U transpose, but inverse the left multiplying the U. That's the only difference. But this is a formal definition, right? By doing so, you can transform between spatial and the spectral domain. Okay. So in our case, we make a convolution between graph structure and the graph singular, which is in the original shape. They are just not relevant, right? One is the 2000 by 2000, one is the 2000 by 1. There's no way you can use the CNN's graph convolution. So that's the benefit of the graph convolution, right? When you go into the spatial domain, make a convolution and go back, right? There's some of trouble, but fortunately we get some of result. I mean, from the convolution. So in the last slides, maybe you notice that there's a g theta, right? G theta of something. Let's go back a little bit. Actually, this is the key of the graph convolution, right? Because how we can make a proper or say optimal g theta. For machine learning users, we want to learn the parameters of g theta, right? But can g theta be anything we want, or can g theta be a neural network or something, right? So there's just a problem. That's a good question to ask. That is how we can design a good g theta function here. And the g theta, if we expand the g theta, it looks like this. It's 2000 by 2000. It's a diagonal matrix. So all the other areas except the diagonal are 0. right? So that's why we can transform between the diagonal matrix into one dimension or transfer back to diagonal matrix. So this is similar to the CNN's convolution, which is the kernel, right? Like the 3x3 pixels, 3x3 weights kernel function, right? So here the G theta is the kernel of a graph convolution, right? So, but however, there's a 200, like a, it is 2000 by 2000, right? So even it is a diagonal matrix, there's a 2000 parameters, which is crazy. I know right now the logic next one is even bigger, but we don't have a, suppose that we are just a small companies. I don't really like the big model because we don't have that much of the computation resource. Right? So to somehow we hate for a model which have so many parameters. So let's see how some of the previous efforts was doing in this domain. And also I select to present the seed word GCN and what GCN is doing is like this. So we are right here, right? We know this is the graph convolution, graph transform convolution, and inverse graph convolution, right? So I will skip most of them. So don't be stressed, because I will release a PDF of everything here, so you can just focus on science. But after tutorial, I promise. So I'm not looking into the equation, especially for most of you guys. If I'm not familiar with this, is a trouble. Just look at the first line of the equation, and the GCN. What the GCN did is that he proposed some of tricks without much of the theoretical justification, and arrive here. G theta equals to 2 minus theta, which is a linear function. It's super easy, right? It's super easy. 2 minus theta, right? You can say there's a parameters 2 and 1. 2 is the bias, 1 is the parameter coefficient of the theta, right? But to be honest, I cannot guide you along the way, but it should be easy. Just remember the conclusion. So if we follow GCN's trick and follow all the way with some simple mathematical transformation, we arrive here. Remember, GCN is proposed from the spectral domain. But if you look at the last line, I highlight here in the red rectangle, you see f plus a times f. There's some physics meaning in the spatial, in the spatial domain. F, which is mean, because originally we have f here. F is the speed information over the neural network. It's the origin data, f, right? A times f. If you can figure out A is adjacent matrix, f is the origin signal. If we times A, if we use the A times f, the physical meaning of the second term is the average of neighbors. Note that A here is normalized. If A is not normalized, it's sum of the neighbors. Okay. So let me just talk in normalize, right? Normalize the version because it's like normal. So you see, we start from spatial domain and going all the way to the end of the equation. And there's some physical meaning in the spatial domain, which means if you perform the convolutions like in the GCN, it is equivalent to use the self-notice feature plus the average of neighbors, right? There's just some of simple assumptions along the transformation or mind assumption, right? So we can interpret the same work in spatial domain and the spatial domain, right? They both have physical meaning. But to be honest, I think people like the physical meaning in the spatial domain, right? Because the spatial is kind of too technical, right? So there's a way, even it is proposed in spatial domain, but we can interpret it in spatial domain, right? So this conclusion, we have reached out to we reach here with the spatial method, but it also makes sense in spatial domain. Also, let's recap the questions we raised right at the beginning, right? So the question for graph is that we have different neighbors, right? A have 5 neighbors, B have 1 neighbors, C have 4 neighbors. So that's why we cannot use a convolution in CNN, right? So that's why we propose a graph convolution. and we, make all the analysis along the way until the last slide. Last slide, the conclusion tell us the spectral method, especially GCN, is equivalent to use its self-notice original representation to plot its average of the neighbors, right? So the conclusion is, I just explain the loss size. So if we perform the GCN, it means I will update A with A. Remember, there's a plus equal, which means A equals to A plus average of its neighbors, right? A plus equal is an average of neighbors, right? And also B doing the same thing, but unfortunately, there's only one neighbor, so it's the number one, right? And C, there's four neighbors, right? C plus its neighbors average, right? So we can also talk back, we can also call back the questions we mentioned at the beginning. That is, we by doing so, you see, because the average of the neighbors, so the result should be in the same dimension, right? Neighbors plus assumption and take an average of them, right? The dimension doesn't change. Right? We just use another way to explain what happens inside the GCN, right? So there's the conclusions. By doing so, yeah, there's a lot of techniques in the spatial domain, spatial analysis and decomposition, graph transform, but finally equivalent to those of things. Just take the assumptions between its original features and the average of its neighbors, right? And that's the benefit of doing so. That is, they are in the unifying dimension, right? So right now, ABC, no matter how you update the ABC with these neighbors, they are in the same dimension, and we like it, right? So the conclusion is traditional graph convolution in CN does not work, but the graph convolution does work because everything here, right? So here's the assumption. So G theta here in the GCN actually is a pretty simple function, which is 2 minus theta. Right? So it's a linear function, right? But actually, technically, G theta here can be polynomial, can be rational, can be exponential functions. I mean, if G theta is in those form of functions, you are good to use any of the graph transform, inverse graph transform to doing so. But if they are not they are not in the pool of those functions, technique is not allowed. Okay. So again, we also call back the G theta. We know GCN use a very simple linear function 2 minus theta, right? And we talk that it's possible to use a polynomial function, rational function, exponential function. But what is the best? What is best? We also want to look into all the graph neural network in the market, right? What the G theta looks like in, for example, the popular graph neural network looks like, right? And also, we want to see, because we interpreted everything in spatial, we also want to look into, okay, what it looks like in both spatial and the spatial domain, right? We use this framework to look into every single, or say selected graph neural network in this tutorial. Right? All right, let's take maybe 15 minutes. If you are good, you can scan the QR code to ask question, or you're welcome to come here to ask question. And in the second half of the tutorial, we will talk about the proposed unifying framework, and we'll show you guys how to use this framework. I will demonstrate, like, I remember like the 6 or 9 models of the graph neural networks. I'll demonstrate how we can use our proposed model to offer more to analyze the graph neural network in the market. So there's some of comparison between them. I think it's good to have because also I want to call back question at the beginning. Which GM model to pick up for your own research or your own CV application, for example, right? I will use this model to analyze the quantitative, like expression powers, and also qualitative, like what's the behaviors in the spatial domain and the spatial domain. All right, thank you guys. Let's take a 15 minutes break, and we'll talk about very soon. 这个人对的。哎，
It's about the notation. What is so the G theta is diagonal matrix.
Yeah.
And how do you this is not a diagonal matrix. So what is theta?
the theta is like if I have the commentary, I can use a 10. So G theta is here. You see that here it's diagonal. 2 minus G theta equals 2. 2 minus 2 and 1, 2 minus C, 2, blah, 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 minus everything. So that's what I mean.
Yeah, but the L here is matrix.
Yeah.
So this is a Laplacian matrix. So so the theta is yeah. So this is like a computer. We have two parameters here. One is left L and one is theta.
Okay, so those are two, let's say that it's in kind of a different representation of the same thing. I'm not sure if I have explained it well that the TC dot TC dot is a non-parametric model, just controlled by the parameter theta 1, theta 2. So this the 2000. It's like a matrix, and the two and the G theta L here. So note that there's some constraint. The G theta is a polynomial. It's a polynomial, which means if we from this line to this side, there's some transformation I skip in this slide. Let me explain. So here, theta actually theta for the eigenvalue. So there's a two format of the GCF. One format is like this. The other format is theta. It's like a 2 minus. Actually, this is not correct. 2 minus lambda. I know it's confusing because sometimes we use a non-parametric, and then here actually is parametric.
So the theta here means different things.
Exactly. So in here, if we know the G theta, which is I don't know what's the type. I'm not using eigenvalue as the input. It can be whatever. There's just a 2000 parameters.
Yeah,
But in a second, but actually, most of the graph neural networks in this way. But we start analysis from this way.
So this one is actually
More like this one. This one. So you see that. So let me use this one because I have assumption that is the GC that's polynomial. It can be rational, can be exponential, can be linear, right? So there's a limited format. So otherwise you cannot do this. So let me see if I can do the numbers. So here is for example, let me use the G theta equals to I'm not sure so it's more easy to understand if I just use or maybe let me see like that. This is the less confusion. So you E, I mean minus take it back here. Two here. You can times identity. And S. I just put the F in the side. So here is actually two.
yeah.
U equals because U transpose. The second term is exactly the
Yeah, the original.
you can do the same thing with the G. Yeah, you can be linear. You can be polynomial. Yeah.
So you give an example of a polynomial.
You could put a 2 minus the power. Okay. It to be learned. It to be learned. I just like we can show you the transformation is legal. Right. So you see, I mean,
still remember. Yeah, let me ignore the theta. Because when we talk about theta, it's in non-chromatic format. But right now we talk about the chromatic, and the chromatic is a parameter is eigenvalue, is the lambda, is the eigenvalue. Because it is in the capital, so which means it's like the eigenmatrix is number one, number two, lambda. Let's ignore F, right? So you, for example, see 2 minus lambda to the power 2 as well, and minus lambda 12 u. Actually, the same thing. U 2. Let me make it u and u square. Well, the trick is this is very easy, right? This is two.
The other one is
Yeah, L square. You know, there's some of trick here. There's some of rules. If it is square, you can just take it out. So u eigenvalue transpose and square, right? So here can be polynomial, can be exponential, can be rational.
So it's not like a polynomial in theta, but a polynomial in the lambda here.
Yeah, polynomial. Actually, that's the problem.
Okay, so both theta and L are not useful in the formula.
Yeah, you can say that. Yeah, but so that's the trick between them.
And the other question is that why is it diagonal? Why is it theta diagonal? Why is it not the full matrix?
Because I'm not sure.
The making of that matrix is the matrix of values. You can compare it with this convolutional network. Convolutional network is not an issue because we're always dealing with the 3x3 pixel matrix. But in graph, we have the graph structures.
Yeah, what I'm saying is that when you
I know
are
your
doing
concern.
in frequency
Yeah.
domain,
Why
why you are doing like convolution in the frequency?
You can see the G theta is a function on the eigenvalues. It's function on the eigenvalue because eigenvalue is a diagonal matrix. So the function of the function of the eigenvalues is supposed to be diagonal. You can ask again. So you see, just ignore the G theta format, which is non-chromatic, right?
Yeah.
We start from there, but we don't stop there. Actually, when we arrive in the final format, it's like a function of
The eigenvalue,
the eigenvalue.
the polynomial eigenvalue.
But eigenvalue is diagonal. Eigenvalue is diagonal matrix, right? Even in practice, when we use the eigenvalue, we can convert it into right? Convert it back to the eigenvalue. It depends on the computation and convenience, right? But the eigenvalue is such a thing in two different formats, right? It can be in diagonal matrix, it can be one vector. Right? To be honest, because it's like in the middle, because we need to perform the gender-wise quantification. So usually, actually, in my personal, I would take the format of the vector format, vector form or eigenvalues. In each way, there's the 2001. I don't really like the diagonal matrix because there's a lot of zero and it's wasted. There's some of mathematical sound, mathematical convenience or something, right? But in
How can you propagate the information from one channel to the other? Is this is it by the polynomial itself? For example, if you just use this, there's no interactions between different frequencies.
Okay.
If you have a polynomial here, it still doesn't have like a propagate information between different frequencies. For example, in the 1D signal, if you are doing convolution in a Fourier transform, you are like combining different frequencies and use the weighted sum to be the
there's some similarity of relationship between the C and S convolution. Let's try to explain it this way.
This is a little bit different.
Yeah. So each of the lambda. Forget about the GCP.
Yeah.
U,
G lambda, yes.
the lambda, and then that's right. So U is the new basics, and the lambda here is the new parameters. Right? This is a new coordinates. This is a new axis. This is new x, y, z axis. And this is the new values on the new x, y, z axis. So it is a way of different.
Yeah.
For example, let me show you.
Yeah, I understand. My question is geometrically speaking, it's like you can only scaling, but not sharing or any other transformations in your frequency body.
Oh, you mean the interaction between different
Yes.
I don't think
So this is just a scaling, right? Because if you do like
Yeah. When we have a new basis, all the parameters for the I'm not sure if you talk about how they.
yeah. Sorry, can we treat them like a different channel? It seems like
I think there
there's no interaction between
CNN.
See, they always interact. You know, you will
Right.
jump
But
over
when
all
you-
the.
Yeah, so before we perform MLP after the graph function, I mean, let's just talk about the figures in the graph function. It seems there's no variety in the graph. We just learn out the parameters for each new base model. So here is I have like 20% for low, 20% for low frequency, 40% for middle frequency, 20% of your frequency, something like that. It seems there's no direct interaction. Maybe I guess if you plug in an MLP, you can let a different dimension, new bases interact with each other. But before MLP, just talk about behavior. It seems as a supply, there's no direct interaction, but you can do the other. Because to be honest, the graph convolution is more like a processor. Because all the graph neural numbers still need to be followed by MLP or something like that. Because it's the representation. After graph convolution, just get an intermediate representation. This is not the final result.
But to me, it seems more like an aggregation function, not a convolutional operator. Because like it's more like you like in a GCN, you just like do a simple mean, right? So simple mean average.
Yes.
And you can do it more like a weighted average, more advanced. And here is just a weighted average in the spectral domain, right?
Yeah.
But it does not do the convolution. Convolution is across different. It's not across different channels, like different frequencies, not just like
Yeah.
ones.
I would say because this is like two types of convolution. There's some similarity in the format, but actually they cannot borrow the ideas across each other. I mean, they are just doing two very different things. We introduced the CN. I want to make some similarity, so to understand this better. But actually, they are doing different things. For example, because the input data we will from convolution is things which are in different formats. It's not like in CN. Right? CN.
No, I'm talking about GCN. Because I'm working on graph networks.
Oh, okay.
Yeah.
Oh, I'm sorry.
Yeah.
If you question, can you scan the code and I can use to talk about? Yeah, I would like to take questions.
Yes.
Yeah, go ahead.
It's about again, but what I understand is like you said it's a convolution graph represented by self plus equal average of the neighborhood, and because that happened because we use the polynomial kernel like to my theta. So if I use another kernel like
Yeah, that's a good question.
different
Actually, there's a different components. Actually,
yeah. So when I use different kernel other than to my theta, so I got a new form of graph convolution that it's not like average of the neighborhood.
Yeah.
Different form.
There's a different. I will talk about it in a second. I will show you. I will show you different format.
Uh,
Not necessarily, not limited to the linear one. I just start on linear one. This is not simple one.
okay.
If every guy says you with that, we can go beyond. I'll show you guys. All right, guys. Hope you have a good rest and let's continue to talk about. So like we said in the second half, because we start with some simple one, right? The linear function 2 minus theta, right? So in the second half, I will show you more complex. I will show you polynomial one, rational one. I will interpret what's the benefit of use a different format function here. So first of all, let's define, because we will talk about it a lot, but let's formally define what's this means by spatial method and the special method, right? Hopefully, if you get some point in the previous slides, I define the spatial method as in the red, right? G theta A, or you can ignore the G theta because it's something else. It's a non-parametric format. It's a G function of A. A here is the graph matrix. It can be graph Laplacian. Right? So, but normally we just use Asian matrix or graph Laplacian. Right? And secondly, we define a special method, which is the G function of the eigenvalue. Right? But actually, they are equivalent. I mean, even they are called special method, but they are the same. Right? Just we just want to study the behaviors on the graph matrix, and also the behaviors on the eigenvalues, and use the sum of the two to analyze its behavior, its performance, its pros and cons. Right? So this is the formal definition. Special method and the spatial method. And by the way, if we perform the special method, we need to perform eigen decomposition first because we need the eigen factors, right? This is the only different thing. All right, so before we talk about our framework, again. Hello. 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 All right. So before we talk about the proposal unifying framework, we need to talk about a little important thing that is normalization and unnormalization. I think it's if people say I have to do normalization, I have to normalize something before I proceed to the next step. It makes sense. It's normalized. It's like a tradition. It's like the some of the necessary step you should take before the next step. But we want to ask question: what's the meaning of normalization? Right? We just don't want to follow the tradition. We want to understand the reason of the tradition. Right? Why we need to do the normalization. Actually, I show you a table, and there's many different normalizations. I think maybe some of you have heard about. They are called random normalization, random walk normalization, symmetric normalization. Actually, just left multiply something, d inverse, right? D to the power -1. Left multiplying something, right multiply something, or both. From both, I mean, both left multiplying and right multiplying. What's the meaning, right? Why we need to do so? Actually, there's many more reasons, but I will give 2 more reasons to perform the normalization. So first, is from the spatial perspective. Suppose we are doing a clustering. Suppose that we have graph, and there's a 2 cluster, and we want to perform a clustering algorithm to distinguish, right? There's a 2 community, right? So I think there's a lot of things along before we can get the arrived equations here. It's from a great tutorial several years ago. So here I just take a conclusion of them. There's a 2 way of them. One is called a radial chord, the other is called a normalized chord. There's some technique inside it, but here's the conclusion. So radial chord just take the number of nodes to cluster graph. You see, just to take a number of nodes
to cluster graph. I have community 1, community 2, and the number of the community 1 and A and B, they are kind of equivalent. Do you think it's a good policy to do clustering? For example, in cluster 1, there's very few link among the nodes. In cluster B, there's a heavy link within each pair of the nodes. It doesn't make sense, right? Use a number of nodes does not make sense, right? And second one is called normalized card, right? This is the formal formulations, but the conclusion is it uses the number of link to cluster graph, which makes more sense. I don't really care about the number of nodes and the size of the company. I care about how close they are, right? How each one in this community connect with each other. For example, you're living in your community, but you never talk about one neighbor. Are you in the same community? Right? So in a spatial domain view, we'll say that the second policy is the number link make more sense. And technically, actually, it uses a normalized adjacent matrix to do the clustering. So this is one reason, right? And second reason is from the spectrum. This is more mathematics. Because, for example, we have the functions on the eigenvalue, right? And the eigenvalues range, if we unnormalize the graph Laplacian, the unnormalized graph Laplacian's eigenvalues range is between 0 and lambda max. And lambda max is less than the max degree of the graph. Suppose we want to learn a behavior across the different graph, some small one, middle one, large one, and they are, mu. I mean, the eigenvalue max are different. I mean, the x is different. Some x is, short, some x is large, right? You see, there's no way you can, or say the dimension of the x are not the same if there's no dimension in a continuous domain. But we can say that the dimension is not the same because the input x range is different. How can you learn some of the, shape pattern across the x, which have different lengths, right? So mathematically, it is not sound, right? So if we use a normalized a graph Laplacian and take its eigenvalue will be fixed into the range between 0 and 2, right? So we can focus on learn out of the shape patterns on the eigenvalues. So that's the second reason of doing normalization. So let's move forward. We will talk about our framework to unify the spatial and the spatial domain and then see what's happening. We will interpret things from both the spatial and the spatial perspective. Let's start from the GCN. We have talked a little about it in the first half of this tutorial, but let's recap a little bit. Because we have defined the spatial method and the spatial method, right? So GCN, if in this format, I just list the equation of at least the key equation for GCN here. And the GCN here is in format of the spatial because it's a G theta of A. It's G theta of A, right? I plus A tier. A tier is a normalized adjacent matrix, right? So we can say that it's a function of, the red part is a function of A. Because I equals to A to the power of 0, right? I equals to A to the power of 0, right? So the right part is the function of A, right? I plus A. And also, if we rewrite it into the eigenvalue, like we show you guys, the purpose is 2 minus the eigenvalue, right? I will take each of the eigenvalue and use the 2 minus its original one, right? And get some transformed new eigenvalue, but it's not eigenvalue anymore. It's adjusted values, right? Because we have a new singular. We need to just adjust the eigenvalue in the new basis, right? So in this way, it is in the format of U, the red part, G functions of the eigenvalues, right? Just a recap. So let's take a close of the equations here. I just put the two equations close to each other. You can see the only difference is this part and this part. So we have interpretations from both the spatial and the spectral domain. We just recap a little bit. So from the spatial domain, it is average the neighbors and the plot itself, right? Makes sense. So from the spectral domain, it's a linear function, so 2 minus eigenvalue. But what it means by it seems average domain is quite understandable, right? But what I mean by linear functions, 2 minus the lambda, right? So let me show you guys. I have maybe some more slide. So 2 minus lambda, which means it's something like this. It's a straight line, right? Because there's a minus before the eigenvalues. So which means if eigenvalues is small, for example, eigenvalue is 0.1, 2 minus 0.1 equals to 1.9. It's scaled up, right? If eigenvalue equal to 2, remember the maximum eigenvalue is 2, right? If eigenvalue is large, it's 2. 2 minus 2 equals to 0. You see, these functions switch the small and big. Why is that? Because the small eigenvalue correspond to the low frequency. The small eigenvalue correspond to low frequency. The signal along the eigenvector changes slowly. So what looks like if high frequency? Let me show you. Let me go back to the slides. I don't have visualization there, but maybe likely I can show you. So here, as a purpose slides, all the eigenvectors actually are smooth. Everything here are the low frequency, because if you start from arbitrary node and go to another arbitrary node, the signal changes slowly. So that's why it is a low frequency component, because this is the first view. And because this is the first 4 of them, right? Its corresponding eigenvalues small. By applying 2 minus lambda, we change the small value to big, because we want a more low frequency. Low frequency, as I interpreted, have some fixed meaning, right? But what high frequency component looks like? It's like you also pick up any node of the graph, right, as a start point, and go to any other arbitrary node. And along the way, you jump a lot, jump high, low, high, low, high, low. What that looks like, it's just like noise, right? So that's why 2 minus lambda, 2 minus eigenvalue makes sense. We want to focus more on low frequency like that. It's more interpretable to the human. Maybe the noise, I mean, the high frequency component makes sense to some genius person, but does not make sense to normal person, right? So it's hard to interpret, right? It's just like a noise, right? Along the way, jump high, low, high, low. What that means, right? Because
So you could say something like it's equivalent to fast filtering.
yeah, exactly. Actually, in the tutorial I cited one paper, but I remember the slides. That paper is I remember is titled as I forgot the full name. It's like in that paper, the author claimed that most of the GCN is just low frequency filtering. But I have a slightly different opinion, right? I admit that most of them they are, because this is the reason of the data we're using. For example, I guess most guys here are doing CV, right? Take a image 2D image, right? 2D pixels. If you take any pixel, suppose it's a photo or something, right? Take any pixel. It's good to assume most of the pixel around this slack pixel are similar to the center, right? It's a photo, right? I know there's some special case, but in a photo, it's like this. It's smooth, right? Also, you can pick any of a pixel from start with and pick any pixel to end with, and just try to get a trajectory between them. Along the way, the signal changes slowly. It changes, but it does not change, pretty high, pretty low, pretty high, pretty low. Maybe there is some case, but in normal photos, it's like in the low frequency domain, right? So similar in the graph. But I will show you some of different case. I'll show you, okay, most of graph neural are low frequency filtering, but some of them are not, right? So let's continue. So next step, I think. All right, so here. So right now we have finished the normalization, and we know the case study with GCN, right? We explained a lot in the first half of the tutorial, and right now you get a point of how we can interpret the GCN in both ways, right? So average neighbors equivalent to linear function equivalent to, we just focus on, we want to focus on the low frequency component, right? So the very easy interpretation. So I will go through some of the select work one by one and show guys, or maybe demonstrate most of the graph neural can be analyzed under our framework. The second work is graph stage. I think this is also one of the most popular GN, right? If we use the mean aggregator, if you're familiar with that, forget about it. Right? I just use one configuration in that paper, and the analysis, what graph stage looks like, exactly equivalent to the GCN. The only different thing I want to say that is the normalizations of the A is different. That's the only thing. Right? So in theory, they are the same. It's I minus I plus A tiered is the normalization. Right? If we don't distinguish the difference between different normalization, they are the same. Right? And the last work I want to demonstrate is GIN. GIN is one of the papers how powerful on graph neural network. Right? So if we write into the same format, functions of the graph matrix, it looks like this. It's 1 plus epsilon times A plus A, times I plus A. So you see the only difference is there exists a control parameters, hyperparameters you can tune. I remember in the papers, it just changed the eigenvalue to some small values like 0.1, 0.3, 0.1, 0.2, 0.3. Right? So if we change the control hyperparameters, we just change the ratio of I and A. I means itself, A means its neighbors. We want to change the weight of, because when we, sum up myself or self node and my neighbors, I want to, change. I want to have the flexibility between myself weight and my neighbor's weight, right? But before that, I mean, GCN and Grossage, just take an average. Me and my neighbors, same importance. But GI here, I want, give more importance on myself. And that's it, right? So it's just another ratio between the self node and its neighbors. So we have introduced the GCN, graph stage, and the GIN. So let's rewrite everything in eigenvalue, right? Remember the 2 minus the 2 minus the lambda, right? This is maybe too small, but let me read it. So GCN is 2 minus lambda, graph stage is 2 minus lambda, and the GIN is 2 plus epsilon minus lambda. So right now, we get a point that why we need to perform a 2 minus lambda, right? But what's the physical meaning if we put a epsilon here? 2 plus epsilon minus lambda. So the bias term is a little bit higher, right? A little bit higher. So let me, so which means if a small value, let's suppose. So if a small eigenvalue, suppose it is a 0.1, right? 0.1 small eigenvalue, which correspond to low frequencies, right? 0.1, 2 minus 0.1 equals to 1.9. Here I plot the sum of small eigenvalue. Oh, sorry, small epsilon value, which means beyond the first work, GCN, the graph stage, GIN want to put more weight on myself. Or say put more weight on the low frequency domain. Okay. So if you increase the epsilon, there's more weight on low frequency domain. So relatively, there's less weight on the high frequency domain, right? So that's the interpretation. So next is a case study of the deep work. I think it's very efficient work of graph neural work, but it is a proposal from the spatial domain, not from the spatial domain. So let's see how we can interpret a spatial domain graph neural network in spatial domain. So this time we're doing reverse, right? So random works pretty easy. So first, it's like showing down below in the slides, we'll just draw many of the random works in the graph, right? We pick up any of arbitrary start point, the end point. We draw as many as possible. We draw as many random works as possible and perform word to vector, right? Word to vector. Suppose the maximum window size is 2 plus 1. Suppose you can change the value. So it's 2 plus 1. And because there's a center node in the middle, right? 2 plus 1. So there's a T before the node, T behind the node, right? So T. So you see there's 2 plus 1, which means if I am the center word, I can reach out at most the neighbors, which is T hop away from myself, right? That's a T hop, right? So follow the random work kind of theory. If you can reach out the first order neighbors, which means your direct neighbors, its transition possibility is just the A. Of course, you need to take normalization, right? So D to the power of -1 times A, which means the transition possibility of one node to reach out any other node. If you don't get a point, just remember the conclusion, right? And A to the power of 2, which means the transition possibility or probability one node can reach out the second order neighbors. A to the power of 3 means one node can reach out, to the third order of neighbors. So if suppose we can, draw as many random works as possible, and suppose we have like an equal number of different lengths, right? Length of the random works. So this is A denotes the transferability to the first order, fourth order neighbors. A spell the second one, and so on. And until A to the power of T, which means we can reach out the transient probability to reach out the T order neighbors, right? And because it's random work, right? We sum them off and take the average of them as the updated features, right? So this is like we have still some of a minor assumption. We assume like each type of length of the rainbow take the same probability. So that's we just we don't take any parameters or coefficient before them. So let's rewrite another one, JBNet. Actually, this is seed work, right? It's a seed work of GCN, right? So ChipNet is just directly applied so-called chip-shape polynomial. So it is polynomial. It is polynomial. In previous work, you see the deep work, right? Deep work, it is polynomial, right? It's polynomial of A. I equals to A to the power of 0, right? A square, A cube, and so on. So it is a polynomial function of A, right? And the second one, the ChipNet, because of the direct applied the chip-shift polynomial, just a special type of polynomial. It is polynomial. Right? And the last one I want to demonstrate is the node vector is kind of different random work, right? But there's some special policy to perform the random work. I'm not sure if this is too small, but let me read it. So there's 3 rules under node vector. So first one, there's 1 over P probability to return to the source. I mean, because it is propagated, it's a random work, right? I mean, they never go out. It takes 1 over P probability to return itself, which means there's nothing happening, right? And there's a one possibility. It is not normalized. I mean, their possibility is not normalized, so they don't sum up to number 1, right? So there's a 1 possibility, 1.0 possibility that the random worker perform BFS, search first. So go to the first order neighbors and the second order neighbors and the third order neighbors. Okay? And there's a 1 over Q probability to take the DFS, the depth first search. So if we write everything, here's in equations we want, right? So first we can say, because it's returned to the source, right? So we just put one here, or maybe I here, right? Because I times x, which is equal to the x, which is the original feature, right? Which means nothing happened, right? And oh, sorry, it's 1 over p, the probability is here. And I times x is already featured. If polynomial BFS, because BFS is a broad first search, which means I want to reach out the first order, right? And under this work, it is constrained to 2 hop. There's no 3 hop. There's no other hop beyond 2. So there's a minor assumption, just most of A can reach out to the first order neighbors, BFS, because it can reach out the first of the first. So it will emphasize on the first order neighbors, or say direct neighbor first, BFS. There is some minor assumption. Right? So if we assume this, we just assume most of the BS, just like a performer A times X, which can reach out to the first order neighbors. And about DFS, because the work just constrained the 2 hop, right? DFS can reach out, most of the times we'll reach out the second order neighbors, right? Second, and they go back, and then another second order neighbors. So most of the visit we're on the second order neighbors. So that's why we put a square, which means the transition probability to reach out the second order neighbors. And a minus a, because it's less focused on the first order neighbors. Right? I guess there's a more exact solution, but with reasonable assumptions, we can rewrite like this, right? I guess there's some like a pragmatic coefficient adjustment, but this makes sense. All right, if we rewrite everything like this and make some of a simple mathematical transformation, right? Just skip this one. You can take a look at the last format of the equation. It is the polynomial, but the second order, right? Of A. There's I, like I said, I equals to a to the power of 0, right? There's A and the A squared. Everything is in A, right? So we can summarize this function is also a polynomial, but just with the power of 2, right? So let's write everything here. So in the top half of the slides, you can see it is everything is the polynomial function of the graph matrix, or say the agency matrix.
For the last model, the probability does not sum up to 1.
Yeah. It is not a normalized, it's unnormalized.
So why does it make sense? If it's not
I don't know, but let me see. It's not.
It simply doesn't take into account the self.
Got you. Let's see. Okay. I think so. So this is idea of orders. But if I answer the questions, I would like to say, select the GCN. There's the same trick. We don't care about the scale of the input because the neural network can adaptive to any of the data. Because finally, this is an intermediate feature. I mean, after this action, we get an intermediate feature. And after that, we will perform an MLP. So we don't really care about the scale of them. But this is my current opinion. All right. Question? I'm sorry.
No, sorry. In the first one, in the first option, right? Where the deep wall, there are multiple values on the left. So the game value, so the matrix is the A matrix, the other is means not the most right? So when you put in the position, you can also have a game value that are complex. That is quite different from Chebyshev or GCN. So how can you deal with that? I mean, how can you deal with that? So you don't have any more the spectrum between 0 and 2 if you do the normalized.
Yeah, but in our code, in normalized.
Yeah.
Okay. So I'm not sure if you can see that clear. I have a tier on the top of the A.
And I've talked about some things before. about the normalization, I assume that most of the rewriting in the normalization form. I know there's some unnormalized form, but it's like in rare case. There's some other meaning. Okay. So if we clear, so let me forward. So we can rewrite everything in first the function of a graph matrix, and the second the function of the eigenvalue. Actually, in terms of the equation, they are the same. Okay, so like I guys, this is comparison between linear and the polynomial, and the linear function just consider if we want to interpret, right, the linear function in space domain can only get access to the first order neighbors, which is direct neighbors. And the polynomial if we can interpret it in the spatial domain, it can access to higher order neighbors. But how high, how many orders you can access is depends on the polynomial functions. But there's a trade-off, right? When you set up a high order of the polynomial, it will take a more computational resource. But it should be more powerful, right? So there's a trade-off. So let's see. So this is the rewriting in the function of the eigenvalue. So linear function is like 2 minus theta, and the polynomial function of different order. In the deep work is the highest order is let's see, eigenvalue to the t, right? Eigenvalue to the power of t, and Chebyshev to the eigenvalue of something, but this is user defined. And the note to vector, the highest order is 2, right? But they fall into the same category of the polynomial, which means they can reach out, people can reach out the t. I mean t order neighbors. Chebyshev can reach out also k order of neighbors, and Novak can reach out most as far as the second order of neighbors. So here, if we interpret everything in linear and polynomial in spectral domain, and they can see that I just give you some example. Right? Suppose the pattern we want to feed is, for example, for the linear function is a 3 times x plus 2, right? Suppose the pattern there is 3x plus 2, and it's of course why not just use the linear function, right? The pattern is like that, but the pattern is too simple to have, I guess, in the reality, right? So if we try to load everything in this g theta, if the function of eigenvalues looks like the second one, it's the x to the power 5 or something, right? You have to use a polynomial, right? Suppose you use a linear function to feed the second signal, what happened, right? So supposed to have a better performance, right? So I think maybe for some of data, maybe it's good to plot everything like this, and you can choose whether linear function or low order polynomial, high order polynomial. Okay. So here we have analyzed the linear and the polynomial. Actually, linear is a type of polynomial because when you set order to 1, right? So I just show you there's the left-hand side is spatial, right-hand side is spectral, and there's a connection between them. And there's a linear, both the linear and the polynomial can interpret it in both ways. And if you change the order number, or increase or decrease, you can switch between the linear and the polynomial function, right? So there's some connections between them. Also, I think a quick point is that we know GCN will check that, which is seed work of graph neural network, right? So GCN can solve the problems something like a 3x plus 2. And the ChipNet can solve the problems like, x to the power of 5 something, right? So there's another question. So what is there exists some other scenarios both linear and polynomial cannot handle well? There exists. So let's skip the GCN because it's too simple, right? It's a linear function. So let's talk about the polynomial, or say the ChipNet. It's a polynomial function. Polynomial approximation in the approximation theory is, it's popular approximation techniques, but there's a disadvantage of the polynomial approximation. That is, it is good at approximate smooth signal. You see, the function I plot in the middle is smooth. But what about jump function? In theory, polynomial functions is not good at approximating this jump function. Right? So what if it's a non-smooth function? You might be wondering why we need to look in this properties. I will give you the spatial perspective interpretation. It is in the spatial domain, right? But I will give interpretations in the spatial domain. So this is a literature conclusion. You don't need to read all of them. I just give a simple conclusion there, right? There's a polynomial approximation, there's a rational approximation. That's the key difference between them is polynomial is cheaper, right? But it's less accurate. Rational is more expensive, more accurate, especially in the scenarios we need to approximate the jump function. Right? Jump function, as shown in this slide, is jump function. In the point of 0, that's a jump, right? There's no way polynomial can approximate function pretty well. If you use a polynomial function, there's a lot, there will be a large error. Right? I'll show you some example. Here is example. There's 3 functions here. The blue one is the target function we want to approximate. You see there's a jump function. And the point around x equal to 0.5, right? In the bottom, right? There's a jump. And the red function is a rational function. And this is the result from the synthetic data. And the result is get by the traditional method. I mean, I use the traditional method to get a parameter, get an optimal rational function as well as a polynomial function. So this is the best rational function can do, polynomial function can do. So you can see what the rate function, the rational function in the red almost overlap with the origin function, with the target function. Yeah, there's some tiny error, right? Especially around the point of the jump point. Right? But if you see the functions, the approximate function by polynomial in the green, right? You see there's a curve, right? If you calculate, if you evaluate, right, using like MSE or something like that, there's much more errors, right? So in theory, this is the benefit of using rational functions, especially in this case. By the way, there's some additional work using neural network to get the optimal parameter of a rational function. There's a traditional algorithm, but this is some work using neural network to approximate a rational network. And yeah, this one paper is in which year is 2002 on 2020. It's called rational neural network. So let's see what's the difference. We have a compare what's the difference between the linear and the polynomial. But here we do something similar. What is the difference between the polynomial and the rational? Right? Why we need to move forward beyond the polynomial? Why we need to have a rational? Is there any benefit? So here, left-hand side, that's my equation. I will skip it. I will just use the conclusion. I just pick one representation work from polynomial, which is the actually this is just it's not a polynomial. It's a linear, but it's type of a polynomial. Another is a rational graph neural network. Let's see what's the key difference between them. Maybe you can tell, right? I highlight the difference in the color. They have the blue one, they have the green one, and only in the rational has the red one, right? PL is the polynomial of L, right? And X is original feature, okay? But the rational function have addition term as the Q. Q is another polynomial. But note that it's a Q to the power of -1. It's Q inverse. It's Q inverse. So it seems we have identified the key difference between them, but what does that mean? So let's talk about them in spatial perspective. So in polynomials, there's often a popular issue of polynomial because it is doing labor propagation. Suppose here we have a pretty simple example. We have 2 nodes, and one node's value is 2, the other node value is 18. And then we will perform a labor propagation, or say just the GCN. We will perform a 1 round, second round, many round. What will happen finally? you're familiar with the over smoothing. If you're familiar with over smoothing, especially when you perform many rounds of the GCN, 2 and 18 will be totally average. Okay, total average, which means after many rounds of GCN, it will become 10 and 10. Which means there's no information you can distinguish those two nodes because they are the same. We just know they are connected. There's no information you can use their updated feature, 10 and 10. Right? First is 2, 18. If you take average for the first time, maybe just a 3 and 17, right? 4 and 16 and so on, so on, right? This is the so-called oversmoothing issue, right? I remember in the original GCN paper, it shows that after 5 times of graph convolution, you got the oversmoothing issue. But the rational one have a different benefit in the red. It's a QL inverse. If a PL polynomial is propagate. Inverse means reverse, right? Because P and Q here are all polynomial, which means propagate. It's label propagation. Inverse, inverse. If Q function has the exact format of P times Q equals to I. I mean, suppose, right? Which means Q just cancel the effect of P, right? But no matter what Q looks like, somehow can cancel a little bit of the effect of PL. So you can intuitively can say P is the pushing the value, but Q is the pull the value back, right? Intuitive. So if we put on a Q, no matter Q, what Q looks like, on the same case, 2 and 18, after many round of the propagation, because there exists one pulling power and one pushing power, there's some balance between. So finally, can reach out and find and 15 and stop it, right? But of course, it depends on the definition of a P and Q. Maybe it can solve with some other balance, but there exists some balance. We're not getting the same issue of oversmooth. So that's the spatial interpretation of the rational function. Also, I want to remind that this is very similar to the residue learning, right? I guess many guys are here are doing CV. Are you familiar with the ResNet, right? Residue learning, and there's also graph residue learning, which means if you see residue learning, it's the same thing, right? Here we have, just look at this finger, the subfinger here, right? It's the prototype of the residue learning. And they just perform the fx plus a. Fx means, for example, convolution or any of operation, right? In our scenario, it's just the propagate. It's a graph convolution or convolution, right? X is the original feature. So in each round of such an operator, I will plot the original feature. So X is always the original feature, right? For example, let me use the CN, right? CN some resonant. Perform of CN plus origin feature, plus another round of CN and plus the original feature, right? So it's never gonna to be over smooth, right? I think this is the idea similar to the rational, right? Actually, similar to our idea, in format, they are the same. In format, they're the same. Do something and plus back my origin feature so that it would gonna never be over smooth. So if we compare, I want to you guys to know that there's a difference because, for example, here, there's some typo. Actually, the top is the rational and then the down below is the polynomial. I want to put out the polynomial we just talked about in the rational, and because there is a sum of similarity. If you see the format, they are all f plus a times a, right? Rational is f plus a and f. Rest of learning is the same. Is the same way, right? F plus a times f. And the polynomial is also f plus a times f. Are they the same? They are not the same. Of course, I'll show you the sign because they are not the same. Because the one key difference is that in the polynomial, here the f is the last updated f. It has been updated. it starts from the last step. But in the rational one, the f here is the original one. The one never changed, the original one. So that's the difference thing. I mean, there's a lot of notation. Maybe there's caused some confusion, but I want to explain they are different. One is the last step, and one is the most original feature. Right? But of course, in format, they are so similar, so it's kind of confusing if you don't take care of them. So I'll show you some of examples in the rational function. So this is something not just proposed by myself, because when I look into the market, there's actually some of the model taking rational way. So one is called a PPMP. It's called personalized page rank, right? So in this work, you can see, let me just use this one, right? 1 minus alpha a times pi. Pi here means A is, of course, is the agent matrix. Pi here, it means is feature. So the first term is the graph convolution. And the second term is alpha times I is the original feature, right? But you see, there's some ratio between one is 1 minus the alpha, and the other is alpha. 1 minus alpha plus alpha equal to 1. So their way to just normalize, right? And the second work is called ARMA. It's from time series. It's from different mechanism. But when we try to rewrite everything in our formulation, we found, you see, the left work and right work, very similar. The only different thing is that the right work is not normalized between the graph convolution and its most original feature. It's A and B. Right? It's not normalized. But anyway, if we summarize everything in these categories, like down below, right? Yellow equals coefficient times green plus the beta times pink, right? Which means when we update the node features, right, in next round, it always equals to some pushing power plus some of pull power, right? I want to mention one thing, that is, this is just one iteration. If we perform multiple such a iteration, it is equals to k order rational function, right? You can also check out later. I will release a PDF version, right? You can check out the paper down below. There's some of series from the time series. I don't quite remember the name. It's called ARMI series, right? When you perform this multiple times, which means you perform k order. You perform k order. So you perform k times of such an iteration, which is equivalent to perform the k order for rational function. Okay. So this I'm gonna take out. Why rational and why not? Of course, nothing is perfect. This is some pros and cons. So here's the takeout for rational. So yes, it can approximate a non-smooth signal, right? But unfortunately, even I have been looking into the problems for several years, so I think it's not an easy question. So basic meaning of a non-smooth function in spatial, right? If I draw any of the like a abstract function of the absolute function or sign function, right? What's the physical meaning in the spatial? I didn't find any of the physical explanation. And second is it can't avoid oversmooth, like I explained just now, right? It connected to the solutions on the oversmoothing. And the last one is approximation theory. And there's in the approximation theory literature, suppose both the one rational and one polynomial, they have a k order, right? If the order is larger than or equal to 5, rational function's potential power is larger than polynomial, which means if rational function is more powerful, the order is likely larger than or equal to 5. Or in our work in the previous one, in this one, you'd better perform at least a 5 iteration. 5 such a iteration to get a better performance. If your graph convolution is less than 5, in theory, there's no way rational functions can be better than polynomial. So, and backward of rational, of course, because it's rational, right? There's some denominator and numerator, and denominator means you need to take an inversion of matrix, which takes, if I remember correctly, it's like a cube time complexity, right? So it will involve a lot of computational resource, and you don't really like it. So, but anyway, this always exists a trade-off, like between the linear and the polynomial, between polynomial and the rational, right? This always exists a trade-off. So let's sum up of the spatial-based graph neural network. There's a linear functions, right? Linear function. There's a polynomial functions of the graph matrix. As well, there is rational function of the graph matrix, right? We just pick three for each category, right? And if we write everything in the spectral, which is functions in the eigenvalue, of course, let's rewrite everything in this format. There's a linear function of eigenvalue, right? Polynomial function of eigenvalue, and rational function of eigenvalue, right? I just demonstrate three of them, but actually, in the reference paper, there's many more. So here is the final. This is the relationship between the polynomial and the rational, right? From both the spatial and the spatial domain, because rational just has an additional denominator, which is inverse of polynomial. Right? If you set the denominator to identity matrix, it becomes a polynomial. So let me show you the complete view of the unifying framework. So first we'll start from the spatial domain, GCN, right? And it's linear function, or say we can call it a local aggregation, because only can get access to the first order of neighbors. And when it goes up to the polynomial, we can get access to many high order neighbors, right? There's some of, if we increase the order, right? There's some switch between polynomial and linear. And for the rational, it's like a self loop, right? Plus the propagation, one pulling, one pushing, right? This is the interpretations from the spatial domain. And also for the spatial domain, we just take a look at the functions of eigenvalue. There's a linear function, and we can change the emphasis on the low frequency domain, right? For the polynomial, we can, take a more complex patterns on the patterns over eigenvalues. And as well, if we use a rational, you can even handle more complex patterns, especially the jumping point, right? So, like I said, there's always a trade-off between them, right? There's always a trade-off between them. So if we go left, right? So the linear one, no matter from spatial and the spatial, they are cheaper. The GCN, right? They're cheaper and less expressive, right? If we go to the right side, to the rational, it's high, it's way, expensive, but it's in theory, it's more powerful. Right? What I can see so far that most work is like around polynomial, right? But this is my personal observation. Some work if they want to avoid over smoothing, can put on some of the rational factors, especially the denominator. But as I so far, I can observe most of the work falls into the polynomial. So the last component I want to talk more details between the spatial and the spatial perspective. I guess many guys should be familiar with the word called word vector, right? So can you hands up if you're familiar with that, or just use it, right? It's famous work, right? Just extract the wording value, right? And even in a graph neural network, especially deep work or random work-based graph neural network, you also use word vector, right? We draw as many random works as possible and perform a word vector, right? But this slide is not related to any of the graph. I just want to show you a perspective between the spatial and the spatial. So word vector, we can call it as spatial perspective method because we only care about the neighbors along the sentence, right? I only care about the neighbors within the same sentence, but actually in practice, we only care about the distance, the sentence within five words, right? We take 5 words, 5 words, 5 words as window, right? We have a slide window. So if I am the center word, I just care about the words two words before me and 2 words after me, right? So we can simply speaking, we say I'm similar to neighbors. This is the strategy of the word back, right? Only care about the local region, but this is a local strategy is pretty useful, right? I think if you have applied word fact, the word embedding extracted by word fact is so performance is so good, right? But the strategy is pretty concise, just to care about the local neighborhood, right? And there's another word, also very famous if with high citation, but back into 2014, is one word to analyze the virtual vector. And the conclusion is that from the perspective of matrix factorization, if we just take the outcome of the virtual vector, actually one matrix is W, which is a word embedding. The other vector is C, it's the context word embedding. This is direct output of the word vector. If we time those two matrices together, it is very similar. There's a minor error, but it's very close to M, which is the so-called shift PMI. It's a concurrence matrix. Concurrence means if one word and word 1 and word 2 appear in the same sentence, I count 1. Right? So which means if we can also do word back from left-hand side, we can also do matrix factorization on the right-hand side. But the right-hand side will involve the matrix factorization, but their results are the same. So which means we can treat the word vector as an approximation of the right-hand side. Right? Right-hand side is a matrix factorization, and the left-hand side is just the main iteration of the strategy of taking the neighbors, or maybe take an average of the neighbors as my updated representation, right? Take a many iteration. So left-hand side is iteration algorithm, but the right-hand side is just one-time matrix factorization, right? The result, they are the same, right? So you can say left-hand side is spatial, local, right-hand side is spectral, right? And the global, right? Because we have an overall picture of the PMI. PMI, of course, is global feature, a global view. And then there's a similar work. If you're familiar with the spectral clustering, I guess it should be very, in the textbook, it should be very popular algorithm to perform the clustering, right? Often it has a very good performance. But let's look at it on the right-hand side. When we perform the spectral clustering, we need to perform eigen decomposition first, right? So I can say it's a spectral method, it's global because I have all the information in the matrix, and I perform the spectral decomposition to get the eigenvalue, eigenvector, and I use the second eigenvector to do the clustering. Right, that's the overall algorithm procedure for spectral clustering. But if we see the left-hand side is a work in 2019, so it's pretty newer. Because the spectral clustering, I remember, it's like several tens of years ago, right? The left side is a 2019 work. It proposed if we can just care about it, I don't want to go too detail, but just take the conclusion. This is the loss functions of their work. It is called a spectral net. It is also perform the spectral clustering. They're doing the same thing. But right-hand side, they're doing matrix factorization. Left-hand side, just do loss function. Compare each pair of nodes iteratively. And because each pair of the nodes, we can call it, local. We just care about each pair of nodes, So in that way, I personally have tried the left word. Also, the paper is pretty good. Have high citations, like several hundred or something like that. It works, and it's even sometimes better than spectral spatial clustering. At least their results are the same. So you see, the same result can achieve both from the spatial method and the spectral method. Right? All right, so the last two slides, I just introduced some possible connection between them. Let's go back to our framework. So we can say that this is some of the comparison very consistent. So methodology, spectral method is more implies the global view, but spatial method implies the local view. Spectral method is computation is like one step, because one-time matrix factorization, but it is expensive, right? For example, 2000 decomposition will involve a lot of space complexity, right? You need to load the memory, right? But for the spatial one, it is iterative, and in each iteration, just care about some of small, data, right? Like a small neighborhood. So the space complexity is lower. But you might be wondering, what about time complexity? It depends on, because the spectral method, space complexity is high, time complexity is high. Spatial method, because they are iterative. Each iteration take a very small, time, small scale of computation result. But you might need a lot of iteration. So that's why I didn't list the time complex. You need more analysis. It depends on, right? Scalability, of course, the spatial method perform the traditional eigen decomposition. It's more stable, right? But the spatial method really depends on the number of iteration. The more iteration you perform, the more closer, or say the quicker you can reach the convergences. Okay. All right, so let's talk about some future direction, not many of them, but we're focused on how to solve the computational problem. So first one, I found if some guys are familiar with the PDE, partial differential equation, it's a very popular tools in the mathematics, but there's many different PDE tools. So here at least two of them. If you see the feature or behavior, they're very close to. I mean, one is waves, the other is diffusion. They are compressions very close to rational and polynomial. Let's see. Actually, this is from a textbook, which is called PDE and Introduction. So it's pretty popular in the preliminary elementary textbook in the PDE domain. So in section 2.5, there's a table that summarizes the behavior characteristics between the waves and the diffusion. So waves, you can see that the information were transported, which means, if there's a let's say, for example, we have pulling power and pushing power, right? If we perform the rational one, we always keep something, right? There's something contained the information we can distinguish the nodes. But waves can also transport this information, also keep the information somehow. But the polynomial, you see, lost gradually, which remind us of the over smoothing, lost gradually, right? So if you perform one time, lost one. Maybe it's good, still keep some information. If you perform many of the diffusions, the information will be average, right? So I found that in terms of behavior, they are similar. So we talk about some mathematics in faculty. I was told by then. I was surprised they are so close. In waves close to the rational and the diffusion close to the polynomial. So there's also some PD work in the graph neural network. I remember in the past several years, but not too many in this year. Right. So I think there might be some of more insightful perspective if we look into the PDE. This, of course, PDE itself is a powerful tool. And most of graph neural so far is focused on the simple graph, which means undirected, unsigned, right? And one link can connect only two nodes or one pair of nodes, right? So what is the theory? What is the tool? Can help us to handle signed, directed, high order, and any other non-simple graph. Actually, I personally take a lot of effort here, but unfortunately, there's not so much of the literature in the past. There's some, I remember some of it in the directive, some of it in the sign, but not as strong as the series in the simulgraph. Right? But people still taking effort on this direction. Right? If I remember correctly, in the direct work in the top conference, machine learning, maybe CV, I remember like there's only 10 or less than 20 papers. And one interesting I want to mention is this is a possible extension. It is called Hodge Laplacian, which means Hodge Laplacian is to model the high order graph. So node itself is called a zero order. Node itself is called a zero order. Node feature is called a zero order information. And the link is called a first order. And if there's a triangle, it can be called a second order. So if we use the Hodge Laplacian, we can see GCN is do something different. So in the perspective of Hodge Laplacian, by the way, if we set the Hodge Laplacian, because there's a parameter k here, which control the, the order numbers of the Hodge. If we set the k to 1, L1 is actually the normal graph Laplacian. So we can extend that 1 to 2 to k, right? Some others. So GCN under the perspective of Hodge Laplacian is actually the zero information, which is the node attribute propagate over the first order of connectivity. And GA is the first connectivity. No matter how it changes, it's a function of connectivity, which means it's the first order information. And X is zero order. So GCN or many of work, as we discussed in the tutorial, it's a zero information propagated over the first order connectivity. So this sentence can be extended, right? Like I write in the bottom that maybe there exists an X GCN, right? Something like that. X order information can propagate over X plus 1 order connectivity. Zero can propagate over first order connectivity. First order can be propagated over second order connectivity. 2 order can propagate in the third order and so on. So this is another perspective in the Hodge Laplacian. And next work I want to mention is the Hodge decomposition. Even they are just named by the same person. I remember the same person, but actually they're doing something different. Hodge decomposition, of course, is based on the Hodge theory, based on the Hodge Laplacian. But most of the work, as I can see so far, is based on the first order Hodge Laplacian. First Hodge Laplacian is normal graph Laplacian, right? So when we perform a Hodge Laplacians, we can decompose the Laplacians into 3 different categories of the dynamics, because Laplacian can describe some type of dynamics, how things moves on, right? And if we can perform the Hodge decomposition, you will get 3 type of subcategory of information. And there's some of terminology, but let me use my word. The harmonic means, which means a small hole. Small hole. Curve, which means a big hole. Right? Which means a big hole. I mean, there's some of a formal explanation. I want to use my simple language. Right? So small hole and the large hole and plus sum of trend. They call it a gradient. Right? Gradient from some place to the other place. Right? So we can decompose something, in a new space, right? But in this new space, there's only 3 categories. And the last one, as I show you guys along the way, eigen decomposition is always incurs a high computational resource, right? So one simple idea is that why not just perform say the distributed computing, right? Parallel computing, right? And another possibility is do the quantum computing. And fortunately, especially when I check out the recent, I found there's a implementation of eigen decomposition in quantum machine learning. I mean, there already exists such a method of eigen decomposition, but of course, there's no, as so far at this point, as I check out, there's no one so far, do the same thing, apply graph neural network with quantum computing for the eigen decomposition, because in the graph convolution there is the eigen decomposition. right? So I think there's a potential advantage to make a good use of a quantum machine and to speed up the eigen decomposition so that we can, take take a special method all the way, because the special method has some of advantage over the spectral method. The only way we can search on the spectral method is the computational, uh, overload, because you need a matrix operation, matrix inversion, and a matrix multiplication. Right? And at least also some conclusion of a time complexity between the classical algorithm to perform eigen decomposition. And the second line is the quantum computing is performed for the eigen decomposition. You can see, at least in theory, it's lower. All right, let's give a conclusion. So from this tutorial, we'll give a definition of spatial and the spectral function. Spatial functions of eigenmatrix, spectral function of eigenvalue, so that we can give the unifying framework along the way. And actually, we have two perspectives. One is along the linear polynomial rational function, and there's some theory conclusions in the approximation theory. More powerful, more computation. Less powerful, less computation, or less accurate. For the computation, we also analyze between the spatial and the spectral, right? There's some trade-off between them, right? So far. All right, so you can continue to ask your questions online, and at least a bunch of the work, if you're interested, check out. There's many more work on the spectral graph neural network. Even today's talk is between the spectral and the spatial, but maybe you can tell slightly more emphasis on the spectral side. Okay? So at least a paper list there, and hope we can have a further investigation in this domain and have better insight for understanding this domain. All right, so I think that's all, and open to any questions so far. Any question? Go ahead.
I heard that there is graph potential network. That's
Graph potential network.
potential.
Oh, graph potential. Oh, okay, gotcha. Yeah, good question. In my tutorial, I select some of them. In my this tutorial is based on my survey paper. Actually, I include attention model, but the format is too complex, so that's why I don't want to include. I don't want to confuse you. So if you're interested, check out the paper. I remember this is the first paper in my paper list, right? There's a complex format. If I remember correctly, it's polynomial, but it looks like ugly. I mean, equation. So that's why I didn't put it on the tutorial. And yeah. Any other questions? So appreciate that. I know this is a CV conference, so I begin to feel weird to come here. This is the first time I come over here, because when I got accepted, I mean the tutorial, like I said, I was like, you are serious? I'm not doing CV, right? But I'm so happy to come over here and talk about people interested in graph neural network. I'm open to actually my past work is open to any of the domain. So I'm so happy to be here, and if you're interested, please feel free to contact me or use the QR code or use any information is available online, and there's a personal website.
Just do theoretical work or what
Okay, so yeah, I'm happy to introduce myself. So theoretical study is one of my work, but how to say that, because if you always perform the theoretical study, people are not so interested in pure theoretical study. So, but this is my personal interest in. So I continue to do this. I don't hope to get much more attention. It's just my personal interest, and I just figure out what's going on inside. And even I take effort for in the past several years, I feel the progress pretty slow, right? So on the other hand, I'm also have been doing some application. The applications cover many domains. So for example, social network. Social network is very easy, right? And you can use synthetic data, you can use reward data, like Twitter. And we have a collaborations with the social science faculty. They are doing real social science, right? Not just like our social science. And from the PhD graduation and until now, I've also conducted some research in urban computing because there exists a lot of data in the transportation network. Okay. Actually, if you have remember in the first few slides, at least some of the fingers, right? Some of application in the graph, you can also apply in the graph brain network. And people are so interested in that domain, and then we have a collaboration in that domain, but with the hospital one. And I personally will move forward with a multi-layer network because I think that will be more interesting. Let me talk a little bit more about this direction. Multi-layer network, I call it multi-layer networks because it seems there's no formal name for this research, which means in our real, society, right? There's a social network, there's a financial network. Financial network means bank to bank, right? Bank to person and something like that. And then there's a disease network, there's an ecological network, right? There's a power network, transportation network, there's many network, right? But I found in each of them, people just focus on its own domain. I mean, transportation person focus on transportation problem. Social domain focus on social network domain. In the power network, we also talk about power network people, and they are focused on the power, domain. Each of them, each of the domain have very unique theory, and they are so immersing with their research, which is good. But you know what? Actually, there's an interaction among all this network. For example, suppose in the past few years we have COVID-19, right? When COVID-19 comes over here, right? It's a disease that come over here. Is it affecting me?
Yeah.
And suppose there's a person get infected, right, from disease, and because he will scale, right, and will maybe believe in some of the rumors, right? He scale and build some rumors, and maybe do not trust the government or something, right? They do some bad behaviors on the social network. Or maybe on the contrary, for example, if people, I'm so strong, right? COVID-19 comes here, never infect myself, right? So I will take the rumor, say that mask does not work. So I didn't take the mask. And I talk to every of my friend that do not take the mask. Of course, it is not, it is harmful, right? So you see, this scenario shows the disease flow can affect the rumor flow. There are different network, there are different things, disease in your body, rumors in your brain, but they can interact. Actually, in the whole system, I believe so, right? When diseases come and the financial network will crash, right? And then the supply chain network will crash. And there's some failure cascade, right? It seems that not too many guys are looking into these directions. I mean, there's interaction between them. Why? But so far, I didn't find any of like theory tools and network. There's some of them in network science, but not in machine learning. If you're interested, check out some paper in network science. They are doing disease rumor what I call co-convolution, co-evolution, sorry, co-evolution. That's many work even in the last year, but they only focus on the disease and rumor. I just wondering why not just extend these good ideas to many of the other network, right? People do need it, right? And now people just look into because people just focus on its own domain and do a good job, right? So
Yeah, thank you for your talk in the first place. It offers very interesting insights. And my question is that for the spectral networks, if you are like linked to a specific set of eigenvectors, so every graph will have its own unique eigenvectors, right?
Mhm.
So like in machine learning area, we just train on one set of fixed weights, right? How does it apply to different networking in this case?
Sorry, can you repeat last sentence?
Yeah, I mean, if you train on network using one set of weights and you want to apply to a different shape, a different graph.
Oh, you
then
mean
will have
transferability,
set
right?
of- Yeah.
Do you
one-
need transferability between different neural network? Or do you want to train neural network from one data and using other graph?
Yes, like train the data on like one set of graphs, like the BCCB or maybe Arizona states, and then you want to suddenly use on New York. And
I got you.
how does it work? Like,
I mean, spectral. I think this is a disadvantage in spectral, right? Because you see, if you, for example, if we change the size of the graph, you need to perform another round of eigen decomposition. And one possibility is that one work I mentioned here. You might be interested in taking a look at this one. Special net here. It can be adaptive to minor number increase. I mean, if you just change a little bit of the number node, the eigenvector does not change much. But if you use the traditional one, I mean, in our special method, we need to first perform the eigen decomposition. I mean, if you perform in that way, you have to perform the eigen decomposition again, and you will see there's a huge difference between the eigen decomposition, eigenvectors before that and after that. So as I think there's no way to do this, but for spatial method, it is easy to transfer.
yeah, for spatial one, we
Mm.
like to use the GNNs because we can train on one set of shapes and one set
Yeah.
of graphs, but use on the other one.
Yeah.
But in the spectral one, it seems like an equals problem.
Gotcha.
Especially sometimes you have a multiplicity of eigenvectors, right?
Yeah.
Like an eigenvalue has multiple eigenvectors, and how you order them is also a trouble.
You mean order the eigenpairs, right?
Like for example, you have one eigenvalue, but corresponds to three different eigenvectors.
How one eigenvalue can correspond to multiple eigenvectors?
Yeah, it's possible.
Oh, it's possible because the eigenvalue is the same, right?
Yeah.
Oh, gotcha. But since the eigenvalue is the same, so the eigenvectors are the same, right?
No,
They are-
eigenvectors may not be the same. You can have multiple.
Oh, really?
Yes.
If the matrix is not a full length, then you can get multiple eigenvector.
Oh, yeah, I didn't know.
Oh,
I'm
I
not
really
aware.
know why the case, because you are using the Laplacian matrix, which is real and symmetric, and this is not going to happen.
Oh, really?
But
Oh, it's good to know. But I didn't. I'm not aware of this part, but this is good to know.
yeah, but the trouble is that if I have eigenvalue 0, I can have multiplicity.
Oh, yeah. That's
Even in this symmetric case, I will have this trouble.
yeah, that makes sense. Because when you have a multiple zero eigenvalue, but should be a disconnected graph, right? You have a 3 zero eigenvalue, which means you have a 3 disconnected component as a special series shows.
Because I'm actually not working exactly on the Laplacian.
You always have infinitely many eigenvectors for eigenvalue, okay? So you may have high dimensional eigenspaces. This is what you mean. You always have infinitely many eigenvectors.
Oh,
Yes,
So maybe it's a complete.
Yeah,
Eigenvector, but you have a symmetric matrix, right?
symmetrical. Yeah, symmetrical matrix.
Okay, so then you have diagonal.
Yeah, graph is symmetrical. You mean
But you somehow perhaps choose some
first of all,
canonical
Yeah.
basis out of them. I don't know how.
No, I think it's a fixed step because you have a fixed matrix. Like if you have 30 by 30, that is 30 items.
If you have two eigenvectors which correspond to the same eigenvalue, then linear combination is always an eigen.
Ah, you mean this?
Okay, so let infinitely many. Even if you have one time eigenvectors are always spaces, so infinitely many always.
Yeah.
Of course, there are situations where you have isolated one-dimensional eigenspaces.
Mhm.
This is
Oh.
actually much nicer situation than if you don't have that. In some sense, but maybe it's not a problem in this case.
Yeah, this is a special case, I understand.
Yeah, it's maybe, as you said.
Oh.
they have that much. They have a special matrix for one
Yeah, that's good to know. Yeah, that's-
Have a dependency on the level of density of your graph, or do we get full connectivity for free here?
you mean the special density?
Let's say you have a graph that is only a chain,
Mhm. Oh, it's a line. It's a line graph.
connected graph.
Okay, for the graph.
The spectral methods.
Mm.
Special consideration for either these extremes or.
Uh,
the same-
So line graph is very special. I didn't do that before, but from the method perspective, it seems because it's adaptive, you need to learn the parameters. So it seems, if I remember correctly, I think only one type graph you need to take care of, that is bipartite graph. So because I remember say when you perform the eigen decomposition, there's a one step. Say I don't quite remember so which step, but it always said except a bipartite graph, you can always perform this whole computation along the way. Yeah, but sorry, I don't quite remember. So that's why that's why I remember bipartite graphs are very special, and I didn't do much about that. I just remember it's quite unique. And if you application may involve a bipartite graph, maybe yeah, you need to take care of. But other than that, I think so all the methods should be adaptive. Right. All right. Yeah.
In between spatial and the vector properties of a matrix is the singular value decomposition of adjacency matrix. So my question is, maybe I missed this.
Mm.
When you go from A to, let's say, the SVD of A, which is UD transpose.
I'm sorry, you SVD?
Yeah, like, for example, you have an adjacency matrix A,
Mm.
and then you take the
SVD.
of it.
Why you want to perform SVD?
I can decomposition of
Oh,
matrix. Then my question is there any representation of the matrix U?
you mean this U in my slides?
Yeah.
I think we have talked about because maybe you missed that part. Yeah, it's at very beginning. When we talk about the eigen decompositions on graph, and there's some interpretations. Let me show you. I guess you are, if I understand correctly, you are. Okay, so you mean this one, right?
This one focuses on the regular value, I guess. My question is about the
Eigenvector. You mean eigenvector?
yeah,
So eigenvector. Right. So yeah, I think this one is kind of confusing because so before we perform any of the like a singular recovery, we need to perform eigen decomposition and get an eigenvalue and eigenvector. And at this point, everything down below is showing the eigenvector. This is the new base. And eigenvalue, you can treat the eigenvalue as just a weight of this basis. Right. This is the eigenvector 0, eigenvalue 1, eigenvalue 2, eigenvalue 3. And if we want to cover any single of them, we need to learn from the coefficient of this eigenvalue, coefficient of this one, and coefficient of this one, coefficient and that one.
so is this similar to that the matrix of approximation using your values? Say that.
Yeah, it's related because after we perform the spectral decomposition, we have eigenvalue and eigenvector. What we're gonna do is we want to start into the function of eigenvalues. Not eigenvectors, but there's some physical meaning of eigenvectors. As I show here, right? So first a few eigenvectors have some physical meaning, right?
And the first eigenvector is the basis, because all red, all zero, or all constant. And in this one, there's all values around Minnesota as capital, right? There's some physics meaning. Anyway, the first few eigenvectors emphasize different places, right? But let's put aside the eigenvector. And the next step, we will talk about the eigenvalues, because eigenvalues is like a coefficient of each eigenvector, right? What we need to do is make a function or adjust the eigenvalue to some other value so that the new value can recover any of the target function. So that's why in the next step, we talk more on the function of eigenvalues. So eigenvector is just like responsible for the interpretability, right? Let's put it aside. And the eigenvalue is the parameter, is the values along the new basis, right? So, and when we talk about the function of eigenvalues, we talk a lot about, because when we talk about the function of eigenvalue, it's a one-dimension function, right? It's one-dimension function. So that's why at that point we can introduce an approximate series, because most traditional approximate series is talking about 1D dimension. And then we talk about different type of function of eigenvalue, linear, polynomial, rational. And in approximation theory, of course, the polynomial is popular. Polynomial is more powerful than linear, and the rational function is more powerful than polynomial. And there's also some quantitative conclusions, like if you increase the order of the what do you call the rational function to 5, right? In theory, it can be better than polynomial, especially when you want to approximate quite ugly singulars in 1D dimension. Yeah, I just recap some of the conclusion. Hope that helped.
There is actually another line of work that doesn't include in our framework. Our framework, when we define the spectral graph neural network, we change the eigenvalues only, right? And in another work, they don't change the eigenvalue, they change the basis, they change the eigenvectors. Yeah, that's a special case that cannot be included in our framework.
Yeah, if you only just talk about another work. If you choose another series of work, actually, you can check out the last slide. Last slide. Last slide. Yeah, it's in the paper list, but there's another series, or maybe survey of the spectral neural network. And I remember reading one of them to summarize. Okay, how about like change the eigenvector? But I don't want to include them because I found in that question that's just very few works, right? But of course, as a researcher, maybe it's good to look into them. Yeah.
May I ask one more question?
Yeah, sure.
Yeah, like you all talk about the a graph, very easy graphs, like weights 1 and then use some social transportation. But in the vision and graphics community, we are more interested in like 3D shape classification.
Oh, gotcha.
3D reconstruction or segmentation. In this case, the actual distance and the angles like between each nodes are also very important.
I'm not the expert, like I said, but I heard some of them may be useful for you. So first, I remember when people are doing 3D, construction, people also they formulated the data in point cloud.
Sometimes also in meshes.
Mesh. Oh, okay, gosh.
Like especially in meshes, it's more similar in this case.
I remember if you, I'm not sure if you're familiar. I remember there's a bunch of work of ground neural network is doing the job 3D constructions on point cloud.
Yeah.
Right. Yeah. But sorry, I don't quite remember that. I have to look into them, but not. I didn't check many of them. I just remember there's some of graph neural that can do so. I think one possibility that we can extend is that it's not by those work, because when you have like an angle of them, right? I think
this is very popular in many other domains. For example, in chemical structure, the angle also does matter.
Yeah, yeah.
So you need to encode the information, for example, so on the edge, right? So in that way, it's not 0-1 connection anymore. It's some complex, maybe matrix, right? Can be tensor, 3D tensor, or some high dimension matrix.
So you mean like a complex number matrix or tens of matrices?
Yeah, complex matrix or tensor
And then
matrix.
we do identity composition of those stuff.
I remember, if I remember correctly, there is a special decomposition in, or maybe they call it like a tensor decomposition, right? I'm not sure the property and behavior is similar, but there's some like tensor decomposition. Of course, it is even higher. I mean, the computation resource is even higher. Yeah.
But you
Sorry.
can see how can they handle the angles?
Uh,
It's very non-intuitive.
I guess maybe we can do this. For example, just to talk about the graph neural network, those I introduced, just use a 2D matrix, right? For example, I'm not sure if we can, for example, if the degree is 75%, 75 degree, something like that. So how you formulate the degrees in your work? Can I say just 75 degrees of the angle? And there's the base and the
The angle is usually just like
Mm.
like a 3x1 vectors defining the normal vector, like the directions. So it's in a 3D space, so you don't have like 75 degrees or anything.
oh, it's not a single number, right?
Yeah, yeah, yeah.
It's multiple number.
Yeah, yeah.
Mhm.
Maybe if you want to have a location that is
Mm.
quaternion or something like that.
Oh. Sorry, but I have no question, right? This is very interesting to look into, right?
Yeah, it's very important to incorporate those information, but it seems like
Yeah, because I have been also working with some chemistry, maybe similar to your question. We're working on how to encode the chemical structure, right? Chemical structure, the crystal structure in 3D, right? So that's angle, but the angle can be described, can be formulated like in 75 degree or something like that. So we can just encode this single value, single one value on the edge, right? The edge is not a 0-1. This is, for example, but this is a bad example. For example, the maximized degree is 90%, 90 degree, and I use 75 over 90 degree as a feature of the link. Right? So that my edges matrix is not a 0-1 all the way. It's kind of 0.5, 0.75, 0.1, 0.12 or something like that. So in that way, maybe so. But if you go to multiple dimension, yeah, I have no idea. But it's a really interesting question. Oh, I want to say if you have you checked about the line graph? Oh, sorry, what is link graph or age graph? Age graph. Maybe that's used for switch the role of age and the node. Switch. For example. If I can remember, let me see. So if there's two nodes here, right? There's a link between them, right? And there's one node link between them. That's link between another node, right? There's a 3 node, but 2 link. Right now, I switch the link, 2 link, right? 2 link, but 3 node, right? I switch the link to node.
Yeah.
You know what I mean, right?
Yeah.
Because so in that way, because you see, in its original nature, you see the X can be multiple dimension, right? And the link, I mean, in those words, right? X can be multi-dimension, but the L can only be 0-1 or maybe fraction number. But if we can switch the age to, it is called age graph. You switch the age and node like that, right? We can encode more information on the age. Maybe that's a way, but that's a drawback because the link can only have one singular value as a feature. So which means in your original applications, original graph or you formulate graph, the original node can only have one feature because it's gonna convert it to a age. Yeah, just my 2 cents.
Like either node or the edge can only have one feature.
Yeah, but based on current technique, but you can also develop. I guess the tensor ideas maybe more lower in terms of research. But if you just use age graph, maybe these ideas can work immediately, right? So it depends on. Okay.
Just a comment. I think in this case, simplicity complex can be very useful because then you take into account not just an edge, but two edges or like the whole triangle.
Sorry, you mean simplicial
The
complex? Okay, gotcha. It's high order, right?
Yeah, exactly. So
Yeah.
then you talk about triangles. And then you talk about
Oh.
triangle, and then you can have one embedding for the whole simplicial complex and not for each edge.
Oh.
Account for the extra time.
Yeah, I think so. Yeah. But high order is often, it's a trade-off, right? It's expensive. I know some are working in the graph neural network, but especially in machine learning. But it seems more work about the simplicial graph is in network science, right? They're more interested about this topic. Yeah, I'm also interested about that. I'm taking the look. It's like I show you Hodge Laplacian is based on the simplicial graph, right? There's a Hodge theory and there's a homology theory, but I'm not taking to the homology theory. There's two theory, two technical direction, right? One is homology, one is a Hodge, for the high order graph. But yeah, I'm quite interested. I'm looking to them, but yeah, it's on progress. It's powerful tools, absolutely. All right. I appreciate your question, and I also learned a lot. And yeah, so guys, thanks for coming here, and hope you guys have the rest of a good day. Thank you.
I want to say like the QR code is not working.
Which one?
The one below.
All
I
right.
want to find this page, but I cannot.
But maybe you
It's
can
like
check
GitHub.
out the
You think GitHub? It is
That's
on
all.
the GitHub page.
already. Oh.
I don't know. I cannot.
But you can also check the what do you call? There's an offshore website, and which will link my page, and then inside which there's many more materials. So for example, let me show you. Give me one.
It's in the tutorial website.
Yeah, there's a link because it's a customized link, which a link to my customized link. Yeah, and there's everything there. Yeah, I'm sorry about that. Oh, how can I make this stupid? Yeah.
Your paper, did you also talk about transformers? The spectral, in the paper you were mentioned during the talk.
Oh.
You also focus on transformers.
Wow, this is I read this papers like 2 years ago.
Oh, okay.
And of course, the transformer is right now is.
You
I see there's a lot of guava
Yeah.
transformer, and I've been looking
have
into.
you ever try to find a way to connect transformers to
And
to spectral theory? Okay, no, it's
you raise a good idea, but I don't have.
okay, no.
You give me a direction.
No, because there are some work.
Really?
Yeah.
Can you share with
Yeah.
me? Yeah, I'm quite interested about it. I think this direction is almost yeah.
Example, this one.
Give me 1 second. I can move wise.
No, because I'm interested to. I'm working on that things.
Okay, let
Read a
me-
lot and just move to hypergraph. I don't know if I'm working on directly hypergraph.
I work a little bit. Right now, I have been collaborating with some of with one faculty,